So today we're going to do a little bit with destructive weld testing. I know we've touched a little bit on it, going through a few things, but we're going to start with some weld fails. What happens when welds fail? You guys see okay?
Yeah.
So we're going to start with poor fit up right away. Huge gaps. A lot of porosity, a lot of slag inclusions. You guys know what causes those, correct? Lack of cleaning? No? Unclean base material? Okay.
Well, no, because we can. Well, I know, obviously.
So first and foremost, just looking at our title here, destructive testing. What does that mean? Let's break it down. Destructive testing, what's it mean?
Putting a weld through like various different durability tests.
Okay.
Putting a weld under a lot of pressure.
Welds under a lot of pressure when it's done up in a skyscraper somewhere. It's pressure is subjective.
Purposely trying to destroy the weld to see how strong it is.
Purposefully trying to destroy the weld to see how strong it is exactly right. We have a given set of parameters. We know that our weld material, based on our AWS code, tells us we're going to stick with 7018, since we've all done stick welding. What kind of tensile strength does our 7018 welding rod have? 70,000 psi of tensile strength. So we have a given parameter that electrode will operate within. Evaluate the quality of weldment using destructive weld testing. Well, first and foremost, evaluating the weld quality is always visual. If something doesn't look right, generally it's going to mean something isn't right. Destructive testing, exactly that. Cars go through destructive testing. Cars have an internal structure that's welded together. Some of those zones are called crumple zones. They're designed to fail within a certain way. It's a specific type of examination where the weldment is destroyed through the testing process. Now, i.e. our guided bend tests that we do downstairs. What else could be a destructive test?
Heat.
Not necessarily heat. What about tensile pulls? Where they actually take the weldment, machine it down into a round rod, and they put it in a machine, and they pull it apart, do a tensile pull on it. Oh yeah, that's destructive, there's nothing left. The weldment is unusable. Two main purposes: evaluate the processes and procedures for specific metals and joints. So the idea of going through this destructive weld test is you're actually going to understand the characteristics of your weldment, what materials you're using for your base, and what you're using for your filler. What kind of voltages, what kind of amperages are you going to run? How much heat can you put into that material before it hits a critical temperature before it fails without a destructive test, i.e. scorching the material. Evaluate the serviceability of a specimen weldment. Can we run this procedure up in a skyscraper, and if something happens, can it be fixed on site, or do we have to, chop and cut and rebuild? Evaluating the serviceability. How easy is it going to be to service this weld? How easy is it going to be to take care of it? type of destructive test is often used in training and testing. Students may be required to pass one or more destructive tests to earn certification. Our AWS D11, you have to pass just one. Whether it's fillet weld, groove weld, flat, horizontal, vertical, MIG, TIG, stick, fluxor, it works. Now, inspectors will evaluate the quality of the test welds through the process outlined by the specific AWS testing procedures. Okay, our AWS D11 that we work with, what do? Milks?
Up and down in strips, depending on thickness, will depend on if it's, depend on the thickness of the strip itself, depending on the thickness of base metal, and then cut off vacuum strips and bend them.
Okay. Now, when we bend them, how do we bend them? We just pick an arbitrary direction to bend them, or are we
That specifies-
testing specific parts of the weld?
That specifies which ones, 3/8 it's facing a root bend, and then, 1 inch is side bends, right?
Correct. Variables, okay, first and foremost, can anybody give me a given number of variables in welding? James?
What was the question?
Can anybody give me a given number, a set number of variables in welding? No, you can't. There are umpteen different types of variables on any given day. You yourself are the biggest variable. Whether you're cold, you're shaking, whether you're overheated, you're exhausted, you're hungry, you're tired, okay? You're uncomfortable, you've got problems with your back, you've got your knee blown out from playing sports, your body sways way too much when you weld. Well, what about temperature, moisture content? Our 7018 electrode, is that susceptible to moisture damage?
Yes.
Absolutely. Is that gonna affect our weld quality?
Yes.
Absolutely. All right, let's see.
GT.
Yes.
I was welding with a 710, and when I took the weld off, the whole, all the slack was cracked.
Okay, well, that's something else, and we'll get to that at a later date. Okay, specific mechanical properties of a weldment may include tensile strength, bend flex testing, impact testing, and hardness testing. Impact testing, okay, that particular weldment, i.e. the picture of the car crashing into a barrier. That's gonna be an impact testing. Military, any of their armor-plated materials, they go through impact testing. Is it going to survive a crash? Is it going to survive a rollover? Can it survive this kind of attack with this type of weaponry? Hardness testing, they will take that weldment and they will actually put it in a machine that will test how hard it is. It's a surface etching. They will go in, it'll push down on it and see how much resistance is in that weld. Bend flex testing. Do we want something when we weld it, do we want it to be rock hard rigid?
No.
No, it's gotta be able to move. Why?
If it's too hard, it's gonna snap, put under too much pressure.
Okay, but what happens especially here in Northeast Ohio, what is constantly changing?
The weather.
The weather.
Hot to cold.
Hot to cold, cold to hot. We can have 3 seasons in a day,
Yep.
okay?
Material's too hard.
Well, if it doesn't have any flexibility to expand and contract, just that force alone will destroy the weldment and actually can cause the material itself to fail. Tensile strength. We know this as a pulling test, right? It's not a pressure test. Ow. To understand tensile strength, it is helpful to think about metal as elastic. Think of it like a rubber band, okay? It's gotta be able to stretch and return. If you pull it past that stretch point, how many of you guys have taken a rubber band and it snaps? flicks you in the face, you get whacked in the eyeball. Okay. This is an example of what happens in a weld test for tensile strength. We've got on the left-hand side an unpulled specimen. Now the key thing to pay attention to is here on the right-hand side. You see how the material starts to elongate? That material has gone past its tensile strength. It is no longer able to return to its original size and shape within a given tolerance. It's been effectively destroyed, and they give you a final tensile strength when it begins to release. Because when they're trying to pull on that this way, it's actually got forces pulling back, and that's how you get your readings. That's the elastic limit.
You a student?
Have a seat for a minute. The transition point is referred to as yield strength. Okay? No, it doesn't mean yield for oncoming traffic. It is yield strength. How much strength or how much effort is yielded in this part. If the load exceeds the yield strength, then metal moves from an elastic deformation to a plastic deformation. Tensile strength test has both qualitative and quantitative measurements. Quantitative, it's a big word. Can anybody tell me what it means?
Quantity.
Quantity, okay, break it down. Qualitative, quality. What kind of work is it? Did you prep the material right? Did you use the right filler wad? Did you overheat your material? Did you follow interpass temperature specifications? Bend flex testing. We do a guided bend test for practice. It's a qualitative, it's a visual test. There's no given number that says, okay, this is 65,000 pounds of tensile strength put on that weld. All we're doing is we're stretching that weld to a known point that it should be able to operate within. It's used to measure the ductility and the soundness of a weld, primarily butt joints. Now, however, we use it for testing groove joints, right? Wrong? Right. Uses a bending jig to test the weld section. Okay, so we have a hydraulic bend tester downstairs. Short, sweet, makes it nice and easy, right? Since the outside of the metal is plastically deformed, any defects will be exposed. Can we discuss some defects? Especially in our hot rolled steel. What do you notice when you start grinding on it, trying to get it down to a proper finish? Is it pitted? Is there any pitting in the surface of it? Sometimes, yeah. Depending on quality of the steel, where it comes from. What else have we noticed about hot rolled?
It's a little, typically it's a little bit thicker than cold roll, it expands a little.
Okay. Generally named for the orientation of the weld in respect to the bending action. Okay, so we have side bend, we have face bend, we have root bend. So this should look pretty familiar, right? The root of the weld. What kind of force is being exerted on the root of that weld? Is that going to be tension or compression? No. Tension, you're pulling on it. Remember, tension is that pulling direction, that pulling motion. The face of the weld, the inside of that bend, compression, it's pushing. My athletes in here, compression, a lot of you guys that play football, compress spinal cords from tackling. Make sense now? Okay. Bend flex testing. This type of testing, they're actually clamping or fixing the test piece and forming it around a stationary roller. Whereas we're pushing our side bend or our face root bend through a set of rollers. Three types of transverse weld bends. We've got our face bend. The face of the weld is stretched. We're pulling on the face of the weld. How well did we tie into the toes? How well is the face of the weld fused to itself? Root weld. This is where it all starts. That first weld. Side bend. It's testing the cross section of the weld. So you're testing all those layered welds within that given weldment in one shot. How well did they fuse into each other? This is Sharpie IZOD testing. It's a measure of impact resistance of the weldment. Gives the toughness and shock loading of the weld. What do you mean by shock loading?
How much force it can take. Just
Okay.
instantaneously.
Can you guys give me an example of shock loading? An excavator busting up concrete. Is that gonna shock load something?
Yeah.
Yeah, because you're pushing down so hard when it finally released, it's all one big smack. Jackhammer's a different animal. That's forged tooling.
What about like glass?
Glass is a good example of shock loading because of the way it splinters. Load is applied rapidly, and in the case of a head-on collision or a seismic event, it's a quantitative test, the amount of energy required for a material to fracture or fail. When prepared with some type of machine notch. Okay, so it's saying seismic. When you guys think of seismic, what comes to mind?
Earthquake.
Okay, what does an earthquake present itself as?
Shake, like a shake.
Vibrations, harmonics. How many of you guys have seen the videos that have gone across the internet where singers have used their voice to vibrate a glass to shatter? Okay, that would fall under this type of test. It is a harmonic test. The Sharpie test, the specimen is supported on both sides and struck in the middle. Okay, so they've got both ends of our piece hit. They have a loaded hammer that's pulled back under X amount of tension, and they're striking the weld right in the middle. The IZOD test, complete opposite. You're only clamping one end. You're only holding on to one end. After that, you're whacking the other end. You're going to test to see if it shatters, correct? Here we have an image of just how that works. Hardness testing. Resistance of metal, typically the heat affected zone. What is our heat affected zone?
Area of the metal that's affected by the heat that's in the current weld.
The area around our weld, where we've welded. The heat affected zone is the area in which the material, the heat has spread to. Tells inspectors if the weld was applied correctly and within given specification. Metal is pierced by a pointed instrument with given load for 30 seconds. Vickers test, it's a diamond-shaped tip. Rockwell testing. Now, it's a conical shaped tip. Now, Rockwell testing is something you will hear a lot of as you go through industry. Rockwell is used as a hardness scale for a lot of materials. The blades in our shear, those undergo Rockwell test. They have to be strong enough to actually shear through other material. It's a quantitative test. Hardness calculated by measuring indentation size. So going back to this, we have a conical shaped tip and a diamond shaped tip. Judging by those two tests, how far it indents based on how much pressure and how long they leave it there, they're able to measure that and tell them, okay, this has this Rockwell setting. Good way to think of this is, you guys remember what 1, 2, 3 blocks are for setting up machining. It's It's a 1 by 2 by 3 inch square block. Okay? When you make those, or if you buy a set, they're gonna come with a Rockwell hardness setting or scale. So that way you can know what you can use that specific tool for. I made a set when I was an apprentice, sent them out, they were made with A2 steel, sent out, hardened, quenched, come back, they were 55 to 60 Rockwell, which is fairly hard. I was able to use them in a press and actually use them to press against steel to create given shapes or hold up fixturing without compressing and deforming. It's all this is really going against, it's the ability to resist deformation. Chemical examination. Chemical analysis is typically used in non-destructive testing, more commonly used as a verification procedure.
This is like acid etching.
Yes, that's exactly right. It's acid etching the surface. They're looking for a change in the molecular structure of that material based on certain parameters. Core sample of the weld removed. Weld sample is chemically examined by expert to verify acceptable composition. Acceptable composition, what does that mean? Have we blended our weld metal with our base metal, right? Okay. Metallographic examination determines the distribution of non-metallic inclusions, grain structure of the weld and fusion zone, and the extent of the structure of the heat affected zone. Okay, what this is telling you is how much have you changed or modified that original grain structure of that material that affects the strength and rigidity of that piece, correct?
That's why you don't wanna quench it in water either.
Certain processes, yes, you do not want to quench it in water. What else can affect grain structure in heat affected zone?
How much heat is put in, how much time to cool down.
Okay, how much heat put in? How much heat did we put into that piece? Did we scorch metal? Oh, absolutely, like grandma's cookies. This is where we start getting into our weld procedures, following that set of instructions. First and foremost, we have a visual examination. Macro specimens chemically etched to bring out structure. Examined by unaided eye or with a magnifying glass. All we're doing is doing a visual inspection. Microscopic examination. Specimens are polished and etched by a standard procedure. Structure examined under high-powered microscope. Okay. Now, destructive weld testing. Are you going to build a roller coaster out of Cedar Point?
No.
Walk up to it and arbitrarily pick a section. I want to take this topmost part before it drops on the really big drop. I want to cut it out and test it. No. What are you going to do?
Simulated by using a separate piece.
Simulate it by using a separate piece. Okay. What else?
Maybe test it before it's all put together.
1 second, gentlemen. We got thank you.
Do you think that would be good enough?
Oh, you guys did it wrong.
Today?
Yep. We'll discuss here in a minute. I'll be out in a second.
Alright.
You're gonna take trimmings of your original material, right? You're gonna follow your WPS, right? You're gonna go through all the steps that have to be done, following interpass temperatures, all the pre-process, post-processing steps that are required. You're gonna send that specimen out. You're not gonna go cut apart a finished object, right? So moving forward, we're gonna start a groove test. Doing that groove test, we will go through it step by step. Each step will be a different well, different sequence, different set of parameters. Everybody good with that? All right.